So we're going to find the linear speed of an object traveling in circular motion. So suppose we have an object that moves around a circle, radius r, at some constant speed. So if s is the distance traveled in time, t, not sweet t, but just t, around the circle, then the linear speed v, so the linear speed v of the object is defined to be v equals s, the distance traveled, divided by t, the time it took to travel around the circle. Okay? Now, the angular speed, omega, this is a Greek letter, okay? Omega, typical for angular speed of this object, is the angle theta, okay, swept out, divided by the elapsed time t. That is, omega is equal to the angle divided by the time. Okay, so in a picture, what's going on here? So we've got some central angle, and we've got a circle with radius r, and we've got this object, okay, and it's traveling along this curve. So it travels some distance s, okay, and that angle, that central angle theta right there. And when we start here, time is equal to 0. But as I go through, I get to here, the time is equal to t. So after t minutes, seconds, hours, however long, whatever the units are, that's where we're ending up. And we want to know, what was our linear speed v to get there? It's the distance traveled divided by how much time, okay? So angular speed is the way the turning rate of an engine is described, okay? For example, an engine idling at 900 RPMs, maybe you've heard of that before, 900 RPMs, that's revolutions per minute, is one that rotates at an angular speed, 900 revolutions per minute. What is this equal to? That's equal to 900 times revolution per minute multiplied by what? 2 pi radians over 1 revolution, right? I have to go 2 pi radians to go through 1 revolution. So 1 revolution cancels to 1 revolution here. And what do I get? I get 1800 pi radians per minute. Okay? So there is an important relationship between linear speed and angular speed. Linear speed, okay, this is equal to v, is s divided by t, but what is s equal to? To find this distance s, I multiply r times theta, right? So I replace s with r theta, and it's still divided by t here. Okay, so what is this equal to? This is r times theta over t. Well, guess what? Theta over t is omega. So this is r times omega, all right? So this last formula here, linear speed, v, is equal to r omega, where omega is measured in radians per unit time. So if time is in seconds, then you put it in seconds, whatever your unit time is. Okay? So let's work through a problem together. All right? So we got a kid. A child is spinning a rock. Okay? So let's see if I can get this typed out. All right. See if that's right. So a child is spinning a rock at the end of a 2-foot rope at a rate of 180 revolutions per minute. So that's RPM. Okay. And now I want to find the linear speed of the rock. Okay. So first off, I need to figure out, okay, so the rock is moving around a circle of radius 2. So if you think about it, you got your little kid, right? And he's, I don't know, maybe he's playing Yippee-ki-yay, right? And so he's flipping this thing around. He's spinning this rock around in a 2-foot diameter or 2-foot radius, right? So the radius is r equal to 2. He wants to know, how fast, what's the linear speed of the rock when it's released? So as soon as it gets let go, okay? So what is my formula? Well, my formula is V equals R omega, right? So how do we do this? Okay, how do we do this? Well, first I got to figure out what the heck omega is. Okay, so omega are the radians per unit time. So how do I get that here? Well, I need to take my revolutions and I need to turn it into what? I need to turn it into radians, okay? So I have revolutions per minute. So omega is equal to 180 times revolutions per minute, okay? Which is equal to what? This is 180 times revolutions per minute multiplied by 2 pi radians per 1 revolution. And what do you know? Those cancel and you get 360 pi radians per minute. Okay. So that's my omega. And so now all I have to do is V equals R, which is 2, times 360 pi. And then what are my units? Well, this is feet, and this is radians per minute, right? So my answer is going to be 720 pi. 720 pi and I guess feet minutes. Feet minutes. All right. So one thing to note, if you don't have, like it doesn't say radians out to the side, assume your answer's in radians. If it said like 720 degrees, then that would tell you it's not radians. Okay, so typically for this book and in math classes, if they don't designate what if it's radians or degrees, then we default to radians. Okay, so radians is really what is used the most around here. So 720 pi, 720 times pi, that's basically 2262. 2262 feet minutes. Okay, 2262 feet minutes right there. So the linear speed of the rock when it's released is roughly 2262 feet minutes. Now, I kind of paused a little because foot minutes, I mean, I don't even know what that is. I'm more of like a miles per hour kind of guy. So if you wanted, you could convert this to miles per hour depending on what the problem asks you to do. And just to make sure we're good with unit conversions, right now this is foot minutes, right? Well, what do I know? I want it to end up being miles per hour. Well, feet, there are 5,280 feet. 5,000, I think, right? 5,280. Probably should have known that before. In 1 mile, okay? And something like that. Whatever, it's been a while. And then how many minutes are in an hour? Well, there's 60 minutes in 1 hour, okay? And so the minutes cancel with the minutes and the feet cancel with the feet, and you're left with miles and minutes. So if I multiply 2262 times 60 and then I divide by 5,280, let's make sure that's right. So when you don't know what's going on, just Google, right? So let's Google 5,280 feet. That's 1 mile. How about that? Okay, so multiply that through. You're going to get 25.7 miles per hour. Okay, so that's not too fat. That's not too bad for a little kid throwing 25, 26 miles per hour. All right, guys, lesson here. If you want to throw it a little bit quicker, tie your rock to a rope. All right. Good luck with your homework.